Yeah, sorry for the technical stuff. Yes, you need a bunch of software engineers to handle PowerPoint and a Mac. Always. So, actually, this should be the first slide. Please let me know if you can hear me. I'm not used to speaking with a mic like this. So, OK, so it's 4 o'clock and 2 minutes. And all of you had like 6 or 7 lectures, I guess, and hopefully a big, tasty lunch. How many of you would like a refreshing cup of coffee right now? Raise your hands. OK, cool. A lot of you, everyone almost. OK, so let's imagine for a second that we have our very own coffee machine right here in the room. Even better, we have a barista where you can walk up to him and just request any kind of coffee that you like. You will probably go and say, hi, I would like a cappuccino or an espresso. And the barista will say, OK, go out the back, prepare one for you, serve it to you, and you walk away happy. That's it. Well, I'm here to tell you that we, as developers, can have the same flow, the same process with our clients. We can have the same easy process, one magic word, cappuccino, with our users, with our colleagues. And we can do that by using DSLs. Even more, once we've established this magical word, cappuccino or espresso, we can turn one simple cup of coffee into a variety of cup of coffees. When we walk up to the barista, we didn't say, I would like to have a hot cup of water with 2 sugars and 1 milk. You said one word when you and the barista immediately understood each other because you had a common vocabulary. So I would like to show you during the next 35 minutes that if we establish a DSL or a common vocabulary with our users, with our colleagues, we can enjoy the same of the benefits. So let's get started. Now that we are all awakened from this refreshing cup of coffee, let me properly introduce myself. My name is Alon. I'm working for Wix.com for almost 3 years now, and I'm developing Wix stores, the e-commerce platform for Wix. Let's get started. So the official definition of a DSL is a computer language specialized to a particular application domain. Well, you might ask yourself, how is it different from any other programming language? Well, there are 2 main points. It's targeted at a specific problem domain, and it offers a higher level of abstraction to the user. What does it actually mean? Well, when you're using a DSL, you don't care about the underlying implementations. You don't care about data structures, memory usages, or cloud computing. You only want to get the job done. Another thing, that the fact that a DSL contains nothing more besides the business domain you're trying to solve makes you more focused. With a general computer language, you can model everything and anything. With a DSL, you can model one thing, but in a much more expressive way. Well, basically, these cells are made to fit their purpose only. Let's see a few examples of DSLs. The first one is this DSL from before. I claim this is a DSL because we have here all the building blocks we need to build our common vocabulary. We have our ingredients. We have skim milk, sugar, brewed coffee. We have our units of measurements, 1 cup, 1 teaspoon. Those combined give us a new language we can build and extend and prepare more cup of coffees. Nothing more, only coffees. Let's see another one. Another well-known DSL is MySQL. MySQL is a DSL we all use every day to extract, manipulate, and analyze data. We always use it when we need to solve problems in the data domain. And the last example we're going to see is CSS. CSS is a DSL that allows us to control the way web components look, behave, and feel. So all of these 3 examples I showed you have something in common. They only try to solve solution problems in their specific domain and nothing additional. So this is not the San Francisco Bridge, by the way. I had no idea I'm going to be speaking here. It's just good luck, I guess. So if we take a step backwards and we try to understand the process we and the imaginary barista had, basically it's the same thing we do as developers. We're trying to get from the problem domain to the solution implementation. We get something we need to solve, and we think about how do we solve it. Well, the problem is the road from A to B is not always that smooth. Sometimes it's hard, and it's hard because of complexity. There are two types of complexity: an essential complexity and an accidental complexity. An essential complexity, it's the heart of the problem you're trying to solve. This is the main issue you're trying to tackle. Whatever you do, whichever way you choose to implement the solution, it will still remain a hard problem. Examples are sending a rocket to space, building a search engine, or like even supporting a high log of traffic. Whatever you do, the main stuff remains hard. On the other hand, accidental complexity, it's something we can control. It's something that we bring to our own code because of the way we choose to implement it. Examples for accidental complexities are writing unclear code, over-engineering stuff, and using the wrong tool for the job. So basically, every time we introduce new code or we're working on a new feature or a new product, we are struggling with complexity. And our main goal is to somehow be able to reduce the accidental complexity, because we can't do anything regarding the essential one, but we can control the accidental one. And my claim is that by using DSLs, you can reduce the accidental complexity of your code. You can write less code, you can write clearer code, and you will probably have less bugs. So let's see a few examples. This is a test written in JUnit. Don't go into details, just take a higher look of the test. We have some asserts, equals, we have some default values. Basically, without going into details and diving in, I won't be able to understand what this test does. On the other hand, we have a test written in Specs2. And Specs2 is a testing framework with an awesome DSL. And look at the assertion. We have hello world must start with hello. Hello world must end with world. I can probably go up the street to a homeless guy and ask him, man, do you understand what does it do? And he will probably say, what the fuck do you want from me? And then he will say, yeah, okay, yeah, I know what you're trying to do. So this is the concept. Like, using a good DSL allows us to express ourselves to non-technical personnel as well. So we know that we've seen that what DSLs are. We saw a few examples. And we need a language to implement DSLs on. So luckily for us, this is a Scala conference, and we can use Scala. And Scala gives us some really cool features that will allow us to basically write less of a hassle, less of like bold print code, and pass our intention in a very clear way. Let's see what features of Scala allows us to write a good DSL. So Scala has a very flexible syntax, fit for abstractions. We have optional dots in method invocation. We don't have to use any dots. We have semicolon inferences, optional parentheses. Well, this is way cut off. And we have type inferences. We don't have to mention any type when we initiate a new value. We also have concise lambda syntax, which basically allows us to pass on expressive function in a very minimal syntax. In one line, I can iterate over a list, I can sort it, or I can even do them both. And it's pretty clear what can I do. It's really complicated code in a really small space. Another cool feature Scala gives us are case classes. Case classes are perfect for abstraction, for abstracting your domain object and your business domains. Why are they perfect? Because of two things. First of all, we have default values. We can initiate them with every value we want and remove that hassle from the user. We can also have name arguments. We can easily pass our intention during the construction of the case class. For example, when I initiate name, first James and last Bond, it's really clear what I'm trying to do, James Bond. Also, Scala has implicits. Everybody, I guess, know about implicits, but just to make sure, I'll go really quickly about the features we're going to use later on. So Scala implicits are functions and fields that are auto-wired by the Scala compiler using the matching signature in our current scope. So basically, it gives us implicit conversion from type to type, statically typed, and it allows us to create lexically scoped open classes. which basically mean we can extend the syntax of objects and classes that are not in our direct code base. For example, we can enrich Scala sec, and we're going to do it later on. Some examples for this is like an example for implicit param. I'm not going to go into it. Basically, we have a function that takes 2 parameters. One of those are implicit, and I can invoke it with say hello, George, and the compiler will automatically find the matching value of a greeting and say hi, George. We have an implicit conversion from type to type. So if I have a function that takes only ints and I'm trying to invoke it with a double, I will get a compilation error saying, well, expected int, actual double. Makes sense. If we're going to add an implicit conversion from double to int, we can easily later on just take a double, convert it to an int, and call the function, and everything works. An example for Scala open classes, I guess all of you know this right arrow, right? We use it every day to create like the tuples. And the interesting thing is this is not like a syntax. The right arrow is not like a saved character in the Scala language. It's actually part of the Scala library. It's inside of a final class, an implicit class called arrowsec, which allows us to, which defines 2 right arrows, an ugly one and a pretty one. And basically, every class, every object you have in Scala, you can initiate these methods on, and it will basically allows you to take self A, wherever, and create a tuple with B. So this is an example for Scala open classes. So, okay. We've seen what DSLs are. We know they're good, and that we know they reduce our complexity, and we know Scala is cool. So for the next 20 minutes or so, hopefully less, and we're going to build our very own DSL. So what are we going to build? Well, as I mentioned before, I'm developing the e-commerce platform. And I started doing that like 3 years ago. And we have, like, as part of the solution, we support shopping carts. And shopping carts are coming over in from all the globe. And every country has its own rules, its own tax rules, its own VAT rules, its own calculation rules. And we have a system that supports everything. And it works, and it's great, and we have traits and classes and abstractions, and it's nice. But every once in a while, when I need to go back and like take a higher look at all the logic, it always takes me a few minutes at least to really understand what's going on there. So I thought it would be cool to spend the time we have until the end of the lecture and actually build a very simplistic version of the shipping cart. Or actually, a Go-based tax rule matching system for shopping carts. So let's say we got this assignment, and we met with our company head or our project management, and he's not a technical guy, and he just told us in plain English, listen, man, I have 5 requirements for you. For Canada, the tax is 50% of the cart total. For the UK, it's 12%, but when you calculate the tax, you should ignore the shipping cost. For the US, the tax is 7%. And when you calculate the tax, you should ignore the shipping cost and the discount. Getting complicated. For Finland, it's a really nice country. It's only 5%. And when you calculate the tax, you should ignore the discount only if the shipping cost is larger than 4 euros. And the last one, well, for Israel, it's really expensive. It's 25%. Plus, we have a special tax on tourists, so we're going to add a special tourist tax. So we as good engineers we got these requirements, and we're immediately trying to understand how can we convert those English requirements to system requirements. And we immediately understand that the tax for a shopping cart is calculated by the shipping country. Tax is different for each country, and tax calculation is dependent on other factors like shipping and discount. At this point, we need to stop for a second and remember the process again. We started with the barista and our common vocabulary. We need to establish at this point a common vocabulary between our and the rest of the project teams. If we would have a common vocabulary, we have several advantages. The first one, we're going to have a clear communication between all project teams. I can go to the QA guy, he can go to the product manager, and we will all speak the same language. The second one is our test. We're going to speak the same language we see in emails, in meetings, and everything else. I can actually show my test and my logicals to the domain expert and ask him, man, do I have any mistake here? Is it too complicated? So let's try and break down the English requirements that we got before to actual common vocabulary. We see that we have all the countries we need to support. We see we have fields that will be part of the cart we're going to calculate. We have our verbs. We can either ignore or add stuff. And we have a predicate. We would like to do something, a certain thing only if a certain condition applied. And the last one is we have the actual text that we need to deduct or calculate with. So after we understood what are the parts of the language, let's start to understand how they correlate to one with another. So tax is calculated on a product. Cart is shipped to a specific country. And cart might or might not have a discount. OK, so those are all the requirements we understood, all the relationship we understood. It's time to get dirty and actually start programming. So we start by a basic abstraction and domain model of our business objects. And we're going to start by the cart. A cart is really like simple representative of the actual shipping cart we use at Wix, but it's really, really simplified. We have the cart total, we have shipping, we have discount, and we have a country. Please notice that tax is not a part of the cart, it's a product of the cart calculation. And we have a companion object. We have shipping and a discount, which is just a simple function that takes a cart and returns a specific cart field. So far, it's really simple. The next thing we're going to have a list of all the countries our system supports. Israel, USA, Finland, UK, and Canada. The last thing we're going to use for now is we're going to define several types. And the types are going to represent the relationship between the different objects we extracted so far. So we have the cart predicate, which takes a cart and returns a Boolean. It's just a signature. The text calculator, this is like our final goal. We would like to have a cart and get the actual text from it. And we have a country to text calculation, just a tuple that contains a country and its current text calculator. So using those 3 or 4 objects and classes, let's try and support our first requirement. Every DSL needs an entry point, the place where we start speaking the common language, the common vocabulary. In my example, I chose 4. For me, this is going to be the entry point for every DSL rule I'm going to support. And 4 is just a simple function. It's nothing special. It takes in a country, and it returns a country container. A country container is a simple case class which takes in, in a constructor, a country, and it has our first verb, take. Take is a verb we're going to use, and take returns our actual goal, country to text calculation. And all it does, it basically returns a tuple of a country and a function that takes on a cart and returns the simplest calculation of text you can imagine. Cart total times text. So using this stuff, let's try and see if we can support our first sentence. For Canada, the text is 15%. Well, we have our entry point, 4. We're going to pass in a country, Canada. We're going to then invoke the take verb, the take method with the percentage. And the final result, after we remove all the ugly stuff Scala allows us to remove, is actually for Canada, take 15%. Let's see what's going on under the hood. So 4 returns us a country container. A country container contains the option to invoke take. Take takes in as a parameter the percentage of text you would like to calculate, and the final result is a country to text calculator, which allows us to basically calculate the text for a specific country using a shipping cart. So 1 down, 4 to go. The first part is already supported. The question is, can we support the second part right away? Well, unfortunately, no. Because by the time we finish evaluating the first part of the sentence, we already have our final goal, the text to country calculator. And we need to somehow add an intermediate step to improve the process. So if you would look at the country container, this is the old version, we're going to do a very simple thing. We're going to add a new player to the game called text and country container, which is just another case class, who again allows us to extend our vocabulary. It adds a new verb, ignore. Now we can ignore stuff. And the ignore stuff is a really simple thing as well. All it does, it takes in a count field that we would like to ignore, and when it runs the calculation of the actual count, it just deducts it from the count total. So using this new text and country container, we can now support the second language, the second sentence. Again, for UK, take 12 and ignore shipping. After removing everything, looks like this. Pretty cool. This is actual code. Let's see what's going on under the hood. So this is the same as before. We get the country container. We invoke take. Only now we get text and country container. This is the intermediate step we added. And now we can invoke the new verb we added, the ignore one. So we can now basically ignore shipping as well. And we get our final goal, country to text calculation. The problem is what happened to our first sentence that we supported. If you remember, the final evaluation of the first sentence right now after the changes switched to text and country container. But we would like to have country to text calculation. So how can we fix the first sentence without breaking the second one? Well, this is where Scala implicits to the rescue. We saw that Scala implicits allows us to convert from type to type easily without actually writing any code. So we're going to add an implicit function, which all it does, it takes the text and country, and it returns a country to text calculation, because we already have all the information we had in the first place. We don't need to ignore anything or add anything. This is just a simple conversion from type to type. So after adding the Scala implicit function, this is what happens under the hood. We do get the text and country as before, only now, because we have implicits, the Scala compiler recognizes that we need something else. It searches on its current scope for like a conversion from type A to type B. It finds that we have the function that we added, and it returns the same type as the second sentence, country to text calculation. So let's take a short break and see the process that we've done so far. We got an English requirement. We broke it down to rules. We understood the relationship between every object in those rules. We created the domain abstractions. We implemented some stuff. We broke some other stuff. We fixed it, and we repeated all the process once again, so we can get to the level where all of our requirements are fulfilled right now. Okay. Let's try and solve the last three ones. So now we have the third sentence to support. For USA, the tax is 12%, and when calculating the tax, we should ignore the shipping cost and the discount. And the question is, can we prove the ignore function to take multiple params? Obviously, we can. We have a very simple solution. We can just use a Scala tree called var args and just add a small wildcard to the count field, if you see, the old and the new. And the another additional change that we need to do is, instead of just deducting one count field, it's a sequence now. So we're going around the fold left and accumulate all the stuff we need to do to deduct in our calculation. And this is basically this is all we need to do to support the second sentence. This is what we get. But for USA, take 12, ignore discount, comma shipping. So I'm pretty bothered by the comma, and I think we can do better. And the question is how? Well, let's try and enrich the relationships we have between the different fields on the cart. So far, shipping and discount were just regular fields. Basically, you get a cart and you return some field of the cart. Let's introduce something called count combinator. A count combinator is something a bit more sophisticated, which takes as a constructor a function from a count to a field. And it allows us, once again, to expand our vocabulary, expand our language. Count combinator can support AND. And I need, sorry. So we need the AND to support our third sentence. And all it does is a very simple logic. It takes another one, a count combinator, takes an additional count combinator, and returns a new one where the actual calculation logic combines these two. Okay. We need to change the ignore method to work with the count combinators as well. It's almost the same difference. We're just, again, using count combinators and we're folding left on those. Basically, it's the same idea. And now we can support the third one. We can now actually replace the comma with the word AND. It makes it look much more like English. Okay, but if we try and remove the parenthesis, the Scala compiler will complain that it cannot resolve the symbol AND because it doesn't know the correct order to evaluate different expressions in the sentence. So a cool trick we can do is basically use the ampersand, and we're just going to overload an existing operator of Scala, and we're going to call the same logic that we already have in the AND method. And if you look at it, we can now drop the parentheses and actually get the third line. For USA, take 0.7, ignore discount and shipping, which looks really like English. The question is, why did it work? Like, why does this sentence, when we remove the parentheses, didn't work and the other one does, and the one did? And the answer is the way Scala evaluates its operators. This is actually the order by which Scala compiler evaluates every expression. And you can see that AND is right up the top. So what happens under the hood is basically that now the discount and shipping is being evaluated before the ignore function is being called. And we can safely get our country to text calculation as we wanted. So 3 down, only 2 to go, almost there. Now we need to support a predicate. We only want to do something if a shipping cost is larger than 4. And once again, every time there's a new requirement, we need to find a way to extend our language, extend the vocabulary, and add more additional abilities to it. So we already have the count combinator, which allows us to represent relationship between different count fields we would like to either add or ignore. We already have, we're going to add the if function. And notice this is a capital if, because a small capital if is already reserved language in Scala, and I'm going to talk about it a bit later. It's not perfect. And the if basically does a very simple thing. It gets a condition, and if the condition applies, it returns the count field. Otherwise, it returns 0, meaning I won't deduct anything. I won't do anything. We also add the greater than, so we can control the different logic expression we're going to pass to the if method. This is like the count combinator with everything we've done so far. We started from scratch, and now our vocabulary, our language is richer. We have the AND, the ampersand, the if, and the greater. We can now add a dozen of other operators, and it will just look the same with no changes at all. So after we've done that, we can actually support the last sentence, the fourth sentence, and it looks like this. Once again, under the hood, we first evaluate the discount if shipping larger than 4. This returns us, because the entire thing is composed of different count combinators which you apply one on top of the another, and the final result is also a count combinator. The rest of the calculation remains the same. The ignore function doesn't care that we have this complex logic expression inside of it. We just get the usual country to text calculation. So the final rule I would like to show you, that's just how can we add custom lambda expression, or just more freedom inside of the DSL. So we said that we would like for Israel to add a 25% text. So it's really simple. This is like the basic text in country class we use so far. We have the ignore function that we use so far as well. And now I'm just going to add a new method. I'm going to expand my vocabulary once again. I'm going to add tourist tax, tourist price. And what it will do, it will actually get a function from a count to some decimal, and it's going to add the decimal when we're going to calculate the actual text for that card. Sorry. So this expression is being evaluated. The same process applies, and we get a counting-to-text calculation. So we've done it. We've managed to support all the 5 requirements that we got from our project manager. And this is how it looks like. This is actual code that compiles and works. If you take a look back and compare the English version and the actual code, I'm just going to leave it for a few seconds so you can appreciate the beauty of it. And, and again, if I return to the same homeless guy from the beginning, and hopefully you're still there, and ask him, do you understand what does the right side does? Do you understand what's the logic? Every non-technical personnel can see at the right side, and you will immediately understand what is the logic behind the calculation. This was our goal, to be able to express ourselves, express our code to other non-technical personnel or colleagues. So we've worked so hard to actually build the DSLs. Let's try and use them just for the example. So the first thing you need to do is import the text DSL object. Let's say I put all the code I wrote so far inside of the text DSL object, and text rules are the same text rules we built from before, the 5 rules so far, and we have some random card which is being shipped to the United States. And I would like, again, if I will go with the flow, to be able to say text rules, find rule, card. The problem is, if you notice that find rule 4 is just a Scala sequence, and it doesn't support that syntax. I will get a compilation error. It doesn't know what it does. So once again, we need to use Scala implicits. Scala implicits is a really powerful tool to enrich the language that we are using. So we can just go and add an implicit class that will allow us to extend the regular Scala sec we all know and love, and add a new verb to it, find rule form. This is basically a simple function that takes a sequence of country-to-text calculations and adds another verb to it, find rule form. After I've done that, I can easily run the last line here, and I will get a matching text rule for that card. So we're almost done. The only 2 things I want to talk about is errors and exceptions. We spend a lot of effort making the code look like English and make it feel really, really fluent. But we need to remember this is still code, and code always has exceptions and errors. And it's a good thing. It's a good thing because of 2 things. If we have done our job correctly, and we manage to model every requirement using domain abstractions and Scala case classes, the compiler is actually our best friend. So if you get a compilation error, that means you got like real-time protection from the compiler during actually entering the business rule or the concept that you're doing something wrong. If you're trying to send a shopping cart to a place which does not exist, you will get a compilation error. This is like the best benefit you can get from the compiler. If you model your business rule correctly, you will get almost in real time an indication that something goes wrong. Another one is we need to remember that we still have errors and exceptions and code and whatever. And this is a best practice everywhere, but especially in DSLs, make sure that you're throwing meaningful business exception. Don't throw Stack Overflow. Throw, I don't know, like text cannot be negative. Something meaningful to the end user. This is really part of a DSL because you don't know who's going to be using it. So my final notes. Getting the syntax right is hard. Like if you remember, I told you I had to use the capital F for the for, and I had to use the capital I in the beginning. And I tried really, really hard to get rid of the parentheses, like every time, for parentheses a country. And like after an hour and a half, I said, well, screw it. I understand the meaning. I think it's clear enough. It's a balance. You have to balance between like how good does it look and who is going to use it, which leads me to the next point. A DSL needs only to be expressive enough for the final user. Like we did all this example assuming the user of the DSL is going to be some domain expert in Texas who's going to enter all the text rules by himself. So we worked really, really hard to make it really clear for him and really obvious what should he do. But if we as developers are going to write a DSL that will allow us to auto-wire 8 Google Cloud computing every time something occurs, we don't need to go through all the small details of a comma here and a parenthesis there. we need to do our job. We need to extract the verbs, the adjectives. We need to build the abstractions, and we can care less and less about the syntax because we know that the end user of the DSL is someone who's going to understand the concept of it. And the final note is DSLs are really, really fun, and they're not that scary. Like, it's really hard to get the first line going, but once you do and you get your first line, it's really fun to try and like see how can you extend the languages. Just try and do the simple thing ever, a stupid DSL. In my examples, I didn't use Scala macros, I didn't use abstract types, I didn't use I didn't use like even my implicits. I could have done it so much better because it's not the main point. The main point is understand the concepts and try and see where the language goes to. So I encourage you all, go and write your very first simple, stupid DSL and have fun with it. That's all. Yeah.
I have two questions. One question is, like, DSLs are not targeted for like real developers. So have you come across good tools to create like documentation or Java? Because that has been a problem. Like when I've done DSLs, that okay, you don't need the comma, you don't need the dot. So it's like really good for me. But then who I tell it to, they're like, this is like magic, right? What can I do and what can I not do? Like I can give them some examples, but is there some like good documentation tool?
That generates a DSL automatically? Oh, sorry. The question was, if I understood correctly, is there something that can help us generate documentation regarding DSLs?
You can ignore
Yeah, we worked in TDD in weeks, so like every answer I get like is the tests are the answer because like just look at the test and you will see like all the asserts and what you can do, what you cannot do, basically. I haven't done it, but I guess if you have to give an example to a non-technical personnel, I guess you have to write it down. I'm not familiar with something, I'm sorry.
Okay. And the other question was, so the DSL I did was in Ruby. I've not looked at like DSLs with Scala. Like, did you compare when you did DSL with Scala, any other language or Ruby?
I told you, basically, like, what do you get from, if it's statically typed language, then the benefit that you get is the compilation stuff, that you get, that you know something is wrong during the compile time. But like, if you try and do a DSL, I actually have a version of the same lecture in TypeScript, okay? TypeScript. So it looks pretty much the same, only without the cool stuff of Scala implicits, which is very, very cool. Like for the second example where I can just told you, listen, I'm going to fix it using implicits, and it's like magic, it works. I actually had to add an additional disgusting function called I am just converting it so it will work, because I had no other option. And in Scala, I can just use an implicit. And plus the syntax stuff, if you can ignore dots, if you can ignore the parentheses, like all the options you get, like the clear in the eye. Those are the two benefits I see from Scala, implicits and the syntax.
So one last thing, so with Ruby, I was able to like add AST transformations.
Mm-hmm.
So I guess Scala also allows that.
Yeah. Yeah. Thanks. Okay, thank you guys. Have a good time.